at the outside of the circle, then we will get this dilated.
Is it dead?
Yeah, I think so. We'll get this dilated surface here. So I'm going to point for now. Right, okay, so that's two-dimensional dilation. The equivalent in 3 dimensions is called volumetric offsetting, and that is when we use a three-dimensional input model, in this case a voxel model, and the structuring element is a sphere instead of a circle. So if we take this model here, which I have also brought with me.
But then what's it, just because I know Munir is thinking Department of Commerce for DOC.
Oh, I'm sorry, yeah. DOC is depth of cut. Right, I will explain that in just a moment. So back to offsetting for a second here. If we drag the spherical structuring element along every voxel on the surface of this part, remember the part surface is made up of these little cubes, and then we record the outermost point of the structuring element, we will end up with a surface as shown in the yellow, by the yellow volume there. Okay, so that is an offset, but a contact volume is actually a series of offsets. It is a Boolean union of a positive offset or expansion of the part model by the tool radius and cutting allowance. So first we expand the part model by the tool radius and cutting allowance, where the cutting allowance is some extra material we want left over in the end. We then Boolean that with a negative offset or shrinkage of the stock volume by the axial depth of cut, where the axial depth of cut is along the tool axis, how deeply is it cutting. When we union those together, we get the contact volume. Now, the point of this discussion is that the contact volume is, again, a discretized or voxelized surface along which the center of the ball end tool can reside without cutting too deeply to exceed the maximum axial depth of cut constraint or cutting too deeply into the part model. So just remember, it consists of a voxelized surface, a lot of very small cubes. So that will determine the translational axis positions. The next thing we need to determine is the rotational axis position, and we'll do this with what's called the accessibility map algorithm. So again, here we have the ball joint, and if we want to determine what rotary axis angles are suitable and will not result in a collision, we can position the tool at every point along our tool path and check each combination of the rotary axis angles theta and phi to see if they will cause a collision with the workpiece or the fixture or the machine structure itself.
Could you say that again?
If we put the center of the cutting tool at every point along the tool path and check every combination of our two rotary axis angles and mark those that do result in a collision as blue and mark those that do not result in a collision as white, and we do that for every spot, every step along the tool path, then each what's called map, each one of these is a map, each map corresponds to the accessibility region for each step. So the white area is accessible space and the blue area is inaccessible space. We can then draw an access path through the accessible space with the red line here, and then this plot on the right kind of shows a qualitative idea of what the rotary axis angle progression looks like. So we get a stack of binary bit maps where dark blue in this case corresponds to collision, white corresponds to no collision, and these have a user selectable resolution, so we can change the resolution of the maps in order to determine the increments that we want to step the rotary axes by. Ultimately, after we've done both of these operations here, we end up with a toolpath that consists of many very small, discrete 5-axis movements. So every block will, every line of the program will be one small movement between a voxel with some rotary axis command. When we go to translate this to the machine, we need to talk about the current state of how machine tools are programmed, and that is what's called GCode. So GCode is a text-based numerical control programming language that came about in the 50s actually, and was standardized in the 1960s, and that's very old, but today it's still by far the most dominant way to program a machine tool. So GCode is a serially executed programming language where we execute a text-based program line by line by line. Thank you. And there are two main types of commands in a GCode program. We will have motion commands. These will typically be G codes. And then we will have auxiliary commands, which will typically be M codes. Just for reference, auxiliary commands will be things like turning on and off coolant, turning on and off the spindle. That's not really of concern to us right now. So let's talk about the motion commands, the G codes. There are a couple different types of G codes. Primarily, we have lines, arcs, and splines on some controllers. And when we specify a movement using one of these so-called primitives, we will call each one of these a primitive, we give the machine the endpoint of the movement, and we give it a maximum speed along which it can traverse the movement. So for example, we could give it the endpoint of a line, say move from current position along this line to the endpoint, and do not exceed a speed given by command, which I will explain here. So the maximum speed, we can only go up to this speed, and we can specify the speed in a couple of different ways. There are 3 different codes we can use. Time feed, which means we specify how long we want the machine to take to complete the move. There is feed per time, or kind of typical speed inches per minute. And then there is synchronous feed, which means feed per spindle revolution, and that is if we want to control the chip load on the cutting tool. But for now, we won't be concerned with G95. So newer dialects of GCode actually are a little bit more complicated than simply auxiliary commands and motion commands. We have program flow like conditionals and loops, and we also have what are called CAM cycles, which are peck drilling or things like this that would be a common operation that we would want to represent in one line. In order to actually get the GCode from the CAM system, remember we've planned the toolpath in the CAM system, we will use a post processor. This is a translator that sits between the CAM system and the machine tool. Different machine tools take different types of GCode. They have proprietary formats. They have machine-specific instructions and things like this. So we need different kinds of post-processors to communicate with different machines.
So the program flow includes loops and conditionals?
It can.
What can you access as variables that you could use in these conditionals or loops? Positions, angle, forces, velocities?
Typically, the machine will have what are called macro variables, which will be NC registers that you can store values in if you want counters or if you want timers. You can get axis position, force. I've never heard of a machine that can get force, IO point status, and things like this you can read off.
Power.
Power, sure.
So I can get the position and of all the angles,
Right.
and I can get power consumed, which somehow implies force?
Yes.
So we're using GCode for parametric CAM originally. Here, actually, in order to use GCode for voxel-based CAM, there's some different considerations we need to consider here. So as we said, a 5-axis block, where a block is a line in a GCode program, looks like the one that you see here. So we have G1. G1 means linear interpolation, and capital X, Y, Z, A, and B are axis addresses, and then lowercase x, y, z, a, and b are move endpoints. So when the move begins, from the current position, linearly interpolate to the points on each axis denoted by the lowercase letters here. F is the feed rate address, and lowercase f is the actual, again, the maximum velocity that we're allowed to travel along the path, or the minimum completion time. Both are saying the same thing. And one thing to note here is because GCode is a serial programming language, all of the axes must end the move at the same time. So the speed of the machine may be limited by the slowest axis, which is typically a rotary axis. So even though I may command 10 light years per second, the machine actually won't move that fast. It will only move as fast as the slowest axis is capable of moving. When we're doing this on a voxel basis, here are some examples of what this would look like. We actually draw linear movements between voxel centers, and there are typically 3 different possibilities that we could have here. So this would be one step of a toolpath, would be one movement between voxel centers. We can have the adjacent voxels share a face, in which case the movement distance would be S, or the voxel side length. We can have adjacent voxels share an edge, in which case the movement distance would be square root of 2 times S. Or we can have them share a vertex, in which case it would be square root of 3 times S. Regardless of which move it is, Typically, voxels for a machining operation will be on the order of tens of microns in size, and all of the movement increments here, whether it's shared face, edge, or vertex, will also be on the order of tens of microns. So the point is that the movements will be very small. Translational movements will be very small. Rotational movements will be determined by the resolution of the axis maps, which again is a user-selectable parameter. Once we have planned the toolpath, we will end up with something that looks like this. Here is our ball joint or ball and socket assembly again. I actually brought another one of these. This one doesn't have support structures. So you can pass that around. And so the toolpath will look like the blue blanket covering the top here. So we talked about, we have 5 axes, 3 translational axes, 2 rotational axes. And things get a little bit more complicated when we have these 2 rotational axes because typically, sometimes anyway, they will be attached to the workpiece. So we rotate the workpiece with the rotational axis. And in order to handle this, we use 2 different spaces, tool space and joint space. Joint space is the position of the cutting tool as measured by the axis encoder. So this is the actual axis position with no regard for whether the workpiece has rotated or where it rotated from or anything like that. It is simply the axis position. Tool space is actually reference to the workpiece origin. So this coordinate system rotates as the workpiece rotates. So if the workpiece is attached to a rotary table and we rotate the table, the coordinate system rotates. And the reason why we do this is to make it easier to program parts in 5-axis parts. We can just refer simply in the workpiece coordinate system. We don't have to worry about how that changes.